Good morning. So this is the first in probably a series of tutorials going over this homework. Hopefully it's no more than 2. We might have to extend it to 3. For the most part, I'm just going to put the equations that go with the solution since the numerical answer is already given, with the exception of number 1 where I'll do in more detail. So if you can't get the right numerical answer, even though you have the right equation, it sounds like it's a calculation error or maybe some algebra. If you can't figure out the equation, then that's where you look on here, obviously. Okay, so let's start the first one, which is really a replica of something we did in the notes. Trying to figure out the acceleration of an object rolling down, let's say, an incline. Okay, so if we want to understand acceleration, we know we have to have a force diagram. And the force diagram is no different than one we've had before. We have the normal force, we have F of G, and we have friction. And it's static friction, but I'm just going to put F of F here. So we've done this derivation before for, let's say, a frictionless block or something rolling or sliding down a ramp. And we know that the acceleration, if there's no rotation, is g sine theta. So if it's rolling, then we anticipate that the acceleration is going to be a fraction of g sine theta. And the easy way to understand that is this derivation comes from the net force being just the parallel component of gravity. But since we have a force of friction here opposing it, it's not going to slow it down so much as it's going to go, that force of friction is going to go into providing a torque which makes it rotate, so gravity's not the only thing influeing it, so we can't expect it to be the same acceleration. The easiest way to understand how this is rolling is understand it's rolling about its center of mass. All right, so let's do the equations real quick here. We've got our force diagram, and it's essential you understand that force diagram and be able to replicate it. It's not complicated. All right, so by the linear motion, we know that the net force is coming from the force of friction and the parallel component of gravity. Parallel component of gravity is greater since it's accelerating down the ramp, so it's mg sine theta minus the force of friction, and we know that's got to equal ma. Okay, we don't know the force of friction. We can't say mu mg here. Okay, it doesn't quite work like that. So what we have to do is figure out the force of friction based on how it affects the rotation. So we're going to go to the angular motion part. And we know that the force of friction is providing a torque. So the force of friction times the lever arm, which is nothing more than a radius, is going to equal to the moment of inertia times the angular acceleration. Okay, there's a second law for angular motion. Now, here's where the shape matters. We have a solid sphere, so you can go to your notes and look up that I of a sphere, okay, is equal to 2/5 mr squared. Okay, actually, let me use a capital R here to be consistent. So if I substitute this into here and simplify, I basically get the force of friction. You should work this out yourself. Don't just write down what I'm putting. Is 2/5 mr alpha. Okay, now I'm going to use it over here and apply it to this one. So now I have mg sine theta minus the force of friction, which is 2/5, mr alpha has to equal ma. So I've got alpha and a in my equations, and there's a bridge between those two. We know that alpha is equal to a over r. Okay, got to stick with the capital R. So now this becomes mg sine theta equals 2/5, that's minus 2/5 mr a over r equals ma. All right, and the r's cancel here. So that's good because we see that when we have a right here and here, so if you do the algebra, and I trust you will do the algebra, you'll find that the acceleration is 5/7 g sine theta, just as we predicted. Okay, so the second problem, the homework problem, is basically the same thing, both a hoop. And again, shape matters. If you go to your notes, you see that the moment of inertia for a hoop, okay, is IR squared. Excuse me, MR squared. So it's the same analysis as before. Okay, that's the only difference between this problem and the one we just did. So I have the net force, the force of friction, right, times r, I'm going to the torque part, is equal to I alpha. I is mr squared, and I'm just going to put in a over r for alpha. Okay, I'm just going to do that all in one step. So this becomes r squared divided by r is r, so all the r's cancel on each side, and I see that, interestingly, that F, little force of friction, equals ma. Now I can go back to the original equation, which said mg sine theta minus the force of friction, which is ma, equals ma. All right, solve for a, and I get 1/2 g sine theta. All right, so the rest of them should be pretty straightforward, because once you have the acceleration, the equation for the acceleration, and we put in numbers, it's stuff we've done before. So what is the acceleration of the center of mass? Okay, we're just going to use 1/2 g sine theta, what we just derived. Okay, what's the angular acceleration? Well, alpha would simply be a over r. What is the moment of inertia? Well, we said before, it's mr squared, so you just plug in the information. What's the torque? Tau is going to be I alpha, which is mr squared alpha. All right, force of friction on the cylinder. Okay, so we know that the force of friction is associated with the torque, so we can just say the force of friction is equal to the torque divided by the radius. Angular speed at the bottom, so that sounds like kinematics, so I'm going to use omega squared equals omega naught squared plus 2 theta r. I'm sorry, do I want to use that? 2 theta alpha. Now we can determine where where theta is equal to the distance of the ramp divided by r, right? That's like the sorry that you use in math, except that the s in this case is the distance that it rolls down. Okay, and then lastly, number of revolutions. Well, that's simply going to be your theta divided by 2 pi, right? So number is that. All right, let's move on to the next problem. All right, I'm going to explain this rather than just have you look at it, or at least put the equations. Okay, so we got a ball at the end of a string going in a horizontal circle. So I'm going to draw a simple little diagram, and it's going around in a circle, not very well drawn. Okay, calculate the moment of inertia of the ball. So the fact that it's a ball is not the issue. You might thinking of the moment of inertia of a sphere, but the sphere is not rolling. Okay, it's just twirling around like this. So our pivot point is here. It's not the actual center of mass of it. So it's a simple equation in the sense that it's just the generic mr squared equation for some mass going in a circle. So be careful when you're doing these problems not to confuse spin with moving in a general circular motion. Okay, therefore, what is the angular acceleration? That, if we know the moment, we should be thinking second law. That's tau over I. You're given the torque. Okay, what is a tangential force on the ball? Okay, so if there is a force here, okay, then that's going to be responsible for the torque. So we can say F is going to equal the torque divided by the radius. All right, and after a certain amount of time, what is the angular velocity and the radial velocity? Well, angular velocity, we know time, and we know alpha, so it's simply equal to AT. We're assuming it started at zero rest, or zero speed. And then A, the radial, the centripetal, you could do V squared over R, but since we know angular, we can do omega squared R. All right, moving on. Potter's wheel, we got a force. We've got a omega or an F, depending on how you want to look at that, and we've got an R. So we want to find the how large is the torque on a wheel radius? Well, we can say the torque, we have a balance of torques of the hand equals the torque from the wheel. Okay, so the torque is some F times R, and you just plug in the numbers, make sure you have the right units. So this is going to be 0.06 meters, and you should be good to go. Then how many revolutions will the wheel make in this time? So this is a two-step problem. We found the torque in order to find angular acceleration. Once you have angular acceleration, you can use kinematics to find time. Oh, I'm sorry, that's a different one. I must have skipped one. Oh, I'm sorry. This goes to here. I must have confused that. All right, how much time to stop? So as I was just saying, alpha is the torque divided by the moment. The moment looks like is given. No. Let me double check that. Oh yeah, I'm sorry. It's given right here. Gotta look this over first. And then once we have that, then we can go and find time using, well, let me set it up. Kinematically, the easiest way to do that is if this is revolutions per second, that's going to, omega-wise, that's going to be 10 radians per second. So I would say omega equals alpha times t plus omega naught, but that's 0. So you have that information. And then revolutions, if we use kinematics, I would say theta equals omega naught t plus 1/2 alpha t squared. This is 0. All right, this will give it to you in radians per second. And so once you get in radians per second, so the number of revolutions, let's call that number, is simply theta divided by 2 pi once again. All right, moving right along. Number 3 with the Potter's wheel. All right, we want angular. We got a solid disk, so italicized tells us we got to look up its moment of inertia. We've got a mass, we've got a radius, and then we have a torque. Okay, we assume it spins about its center. So angular acceleration is tau over I, second law. And we want to use the equation I is 1/2 mr squared. Okay, that should be pretty straightforward from there. What is the angular speed after 2 revolutions? So 2 revolutions is 4 pi radians. You got to make that conversion. Now we can use kinematics. Omega squared equals omega naught squared plus 2 alpha theta. All right, we found alpha before. We know the theta. We can solve for omega. And then after 2 revolutions, remove the drag, exerts it how much time before it comes to a rest. All right, should be pretty straightforward. It's just multiple steps. In order to find time, and we're doing kinematics, we know theta, we know omega, we know theta. We want to know alpha. We got to know how quickly it's slowing down. To know that, we need to know the torque, and we need to know the moment of inertia. So we can say alpha, whoops, this is really distorted, is going to equal, let's see, tau over r, right? And tau is going to be 0.05 times 0.1. We're going to need to do a new torque. R is, or excuse me, let's see, that should be over I. It's the same moment of inertia as before. So now that we have that, we should get about an alpha of 0.5 radians per second squared. Plug that into time is equal to the change in omega over alpha, right? That's just a rewriting of the equation we used on the previous problem. Okay, what else we've got? Oh, this is a conceptual one. So why do we use a long, narrow beam? Okay, basically, I'll let you work it out. It has a large moment of inertia. Okay, so you can look up what the moment of inertia is for a long beam about its center. I don't remember it off the top of my head, but the point is, the bigger the moment of inertia, as you're starting to fall with your feet here, okay, this is going to resist turning, so it helps you give time to rebalance yourself. All right. Lastly, softball player. So we got revolutions per second. That's, you got to go to radians per second. Okay, and we are treating the bat as a uniform rod. So that tells you got to look up I for that. Okay, so first of all, angular acceleration, that's kinematics. We don't use the second law here because we don't have anything about the torque. So that would just be the rate of change of angular velocity. If you look up the moment of inertia for a rod like that, it's 1/3 ml squared. Okay, so plug that in and you should get 0.7. And now you can calculate the torque as simply I alpha. All right, pretty straightforward. Okay, last one, and this is related to, oh, I'm going to stop here because my time is just about up. All right, I'll do another one for number 6. Hopefully things are going well. Ask questions through Schoology if you have any issues.